we're now going to talk about analog to digital conversion. The basic principle of an ADC is to use the comparator principle to determine whether or not a particular analog signal is above or not a threshold. In this example, we have a single 1-bit ADC comparison where we generate a reference voltage. So we want to basically convert our signal between 0 and Vref and generate a cutoff point at Vref over 2. And now this comparator will basically decide with VDD equal to 0 if Vin is larger than Vref over 2 or Vout being lower than Vref over 2. So that will effectively perform a 1-bit digital conversion. Now, obviously, a 1-bit conversion might be useful in some sigma delta converters, but we want to have something more complicated. So it is typical for an ADC to use a DAC in order to determine one of the inputs of the comparator. There are 3 basic types of ADCs that we're going to review today: the digital ramp ADC, the successive approximation ADC, and the flash ADC. In a digital ramp ADC, you are going to convert your analog to digital by doing comparison with an ever-increasing digital ramp. So you're going to apply your analog signal on one pin of your comparator, and on the other pin, you are going to create an increasingly larger signal using a DAC and a counter. How does that work? Here's a typical architecture. You will have your comparator right here with your input signal to convert. On the other input, you're going to use a DAC controlled by a counter. The control to your DAC will start at 0 and basically will keep increasing over time, which would create this step response of your comparison for your reference voltage, sorry. So the reference voltage will keep going up, and we're going to use that as a reference for our comparator. With a little bit of logic around that to make sure that we keep increasing, we pulse this counter increase, we'll be able to determine the cut point on this increasing ramp that corresponds to the signal to convert. That way, once you cut the point, you will identify that the signal you wanted to convert is equal to this value that corresponds to this binary comparison on your DAC. So you will start at 0, ramp up to Vref. Once you cross your analog input signal, this is the value that you latch. That is the result of your conversion. The main trouble of a digital ramp ADC is that in the worst case, it will take you the complete time required to ramp up your DAC. So the conversion time is not known up front. It depends on your input signal. There exist other techniques. To avoid that issue, and this is, for example, the successive approximation ADC. Now, instead of ramping the DAC signal linearly, you will be able to apply a little bit more intelligence and use powers of 2s to understand where to stand. So for example, you will have some control logic that will first generate a signal in the middle of the range, and you will identify if you are above or below this signal. If you are above, you will keep refining the second bit and then keep playing with powers of 2s until you have your conversion. The main interest here is that you guarantee that your conversion will be done in a number of cycles x depending on the resolution of your system. Now, another option, even faster, is to use a flash ADC. In the flash ADC, you're going to generate all the references voltages at once and have an array of comparators that will compare at once the input voltage. That way, you will understand where you stand immediately in your complete range of conversion, and you will convert that back into digital logic to make sure your system, to propagate information to your system. Now, I would like to review a couple of notions linked to ADCs. The first one is the notion of acquisition time. And this is the time required for the analog input voltage to be properly sampled inside of a hold capacitance. We did talk about the conversion time. It is the time it takes to convert your sampled data into digital. But before that, you need to make sure that you acquired your analog signal inside of a circuit that is called a sample and hold circuit. It will consist of a sampling switch, so you will sample for a given period of time and then open your switch so that this hold capacitance will keep the signal at a given point of time. This sample and hold circuit is used to discretize over time your signal. Then the ADC will take care of the sampling or the quantization of your signal. A few words about voltage references. The stability of your voltage reference is critical for high precision conversions. And one can use VDD as a reference voltage for convenience, and throw away at least 2 bits of precision due to VDD fluctuation. But others could use commercial reference voltages that will give you extremely precise voltage references to use as your VDD reference to your ADC. Again, this depends on your application, and that will depend on the complexity of your PCB and the type of resolution, type of measurements you have to make.